Okay, here is another water of crystallization problem. This is a little bit different than some of the other ones, and we'll see why. Because right, so here we've got this stuff, ethanedioic acid. Right, so just to explain what that is, ethanedioic acid. Right, it's related to ethanoic acid, which you have come across before. Now, ethanoic acid has got the following formula. If you remember, this is the carboxylic acid group. Okay, and what happens is it loses this hydrogen here, yeah, and you get a negative charge on that oxygen. So when it reacts with sodium hydroxide, you would get sodium ion. This is the salt, sodium ethanoate, right? Right. Ethanedioic acid is similar to that, except it's got two carboxylic acid groups on it. It's got one at that end and it's got one at this end also. Okay, so unlike ethanoic acid, which only loses one proton, this one is going to lose two. That one there and that one there. So it will form this ion. When it reacts with sodium hydroxide or a base, you're going to remove them. And you'll have a negative charge there and a negative charge there. So of course you write that down as this ion C2, the ethanedioate ion C2O4, 2 minus. So if you think what would be the formula of the sodium salt of that, it would be Na2C2O4, and that's what we've got here. Okay, yeah. When you react the ethanedioic acid with sodium hydroxide, you form this salt here. Of course, it's going to be Na2 because each Na has got a charge of 1 plus, isn't it? So anyway, that's ethanedioic acid. It's not a liquid at room temperature, it's a solid, it's a white solid, it's white crystals and they are hydrated. And what we've got to do is we've got to find out what the value of X is there. Okay, so that's a bit of background about what ethanedioic acid is. You might actually remember the dioic acids were used when you form polyesters. You might remember that from year 11. Okay, so let's have a look here then. Right. Now, 1.46 of the ethanedioic acid were transferred into a volumetric flask of 250. And this is a bit different because this is used to fill up the burette. Now, normally, on all the other examples, we have used the solution from the volumetric we've just taken 25 out and put it in the conical flask. This is going to be a little bit different. Let's draw the volumetric flasks there. Um, 250, and we're putting in there 1.46 grams of the hydrated acid. I'll write the formula that way around, H2 C2O4 XH2O. That is then used to fill up the burette. Okay, which is here. And how much of that was used in the titration? Well, it says later down, it says you need 28 centimeters cubed of that. So I'll put that in there, 28.8 centimeters cubed. Right, now what goes in the conical flask? It's right, 25 centimeters cubed of a solution of NaOH of concentration. Okay, so this is a little bit different. So let's put the conical flask here. So here we have got NaOH, 25 centimeters cubed of it exactly, and the concentration of that was 0.107 mole per decimeter cubed. Right, let's just write our two equations up here. So we want conc is equal to moles over volume in dm cubed. And we also want moles is equal to mass over mr. Okay, so let's see what we can do here. Well, we need to work out the moles. Can we work out the moles of the ethanedioic acid? Well, we can't. We've got the mass, but we can't work out the MR because, of course, we don't know the value of X there, do we? So we can't do that. So we can't. That's not the way forward. Can we work out the moles of sodium hydroxide? Well, we can, because look, we have got a volume and a concentration. So let's do that. So moles of NaOH, conc times volume. The concentration is 0.107 and the volume is exactly 25 centimeters cubed, which is 0.025 dm cubed. So that's going to be equal to 2.675 times 10 to the minus 3 moles. Okay, now let's look at our equation. So 2 moles of NaOH react with just 1 mole of that. It's a 2 moles to 1 mole ratio. So moles of our acid, moles of acid then, of H2C2O4, and that, let's remember, that is going to be in 28 centimeters cubed, so I'll write that down there, in 28.8 centimeters cubed. Right, the moles of the acid is going to be half of that. (1.337) times 10 to the minus 3. Okay, so we have a bit of a problem there, because normally, do you remember what we do here is we know that's in 25, don't we? Yeah, that's in 25, and then we want to find out how much in 250. So all we've got to do is multiply it by 10. We can't do that here. It's a bit trickier, okay? So we want to find out how many moles of the H2C2O4 in 250. Now, why do we want to find that out? Well, if we know the number of moles in 250 and we know the mass of that, we can work out the MR of this, can't we? And then when we work out the MR, we can work out X. So that's why we want to find that out. But, well, we've got to do it. How many moles in 250? Well, we've got that many moles. Oops. We've got that many moles in 28.8. So I'm going to say, so this here is in 28.8 centimeters cubed, there are 1.337 times 10 to the minus 3 moles. So I'm going to say, therefore, in 1 centimeter cubed, there are 1.337 times 10 to the minus 3 divided by 28.8. You okay with that? Is that logical enough? Okay, so divide that by 28.8. So in 1 centimeter cubed, and that's 4.64 times 10 to the minus 5 moles. So now we have to say, so in 250 centimeters cubed, there are, well, in 1, we've got that many. So it's going to be 4.644 times 10 to the minus 5 times 250, which is equal to 0.0116 moles. Okay, so now we are at the stage where we know the moles and we know the mass, so we can work out the MR. But that was a little bit more difficult than usual, and all we have to do is 10 times it by 10. We had to do this this business instead, didn't we? Yeah, finding out in one and then times it by 250. So it was a bit harder. Okay, so now let's write down. Right, MR is equal to mass over moles, isn't it? If you do a rearrangement. So the MR of the H2C2O4 XH2O is equal to the mass in 250 divided by the moles in 250. And we've got the numbers there. So we've got 1.46 grams divided by the moles, 0.116, and that's equal to 125.75. So 125.75, let's call it 125.8. So that's the MR. And then we do our usual bit then. Okay, so we're going to write down this formula here. H2C2O4.XH2O. Well, the MR of this bit here is 2 plus 2 times 12 plus 4 times 16, which is equal to 90. Okay, so this bit here is going to be 125.8 minus 90, which is going to be equal to 35.8. So how do we find out the value of X? Well, one water molecule, one water is going to weigh 18, isn't it? So X is equal to 35.8 over 18, which is equal to, well, it's going to be 2, isn't it? What's the exact number? 35.8 divided by 18. Right, 1.98 recurring, okay, and we know it can only be integer values, so X is equal to 2. So the formula of this stuff is H2C2O4. It's got 2 water molecules per molecule of that in the crystal. Okay, so that one was a little bit different. It wasn't just a matter of scaling up to 25 to 250. Just have to keep your wits about you a little bit more.